Hello, this is Dr. Behrang Askarian. I am an associate professor at Washington State University, the Mechanical Engineering Department. I am also a licensed professional engineer in the state of Washington in the area of thermal fluids, PE. This video is another problem in the area of external flow over a flat plate. Before watching this video, I encourage you to watch those two videos where I explained the difference between the local friction coefficient and average friction coefficients. And I also categorize all these problems, external flow over the flat plate, into 5 different categories. And I provided all the equations for every case. So you watch those first, then come back and watch this one, because we have to determine what category this problem falls into. And when I say category whatever, then you know what I'm talking about. If you already have watched those videos, then we're good to go. If not, the links are in the description. Okay, so let's take a look at the problem and let's see if we can solve it. Go ahead, read the problem. Okay, so this is cast iron. I already got the value for epsilon for cast iron from a table from fluid mechanics books. It's 0.26 millimeters. We have to convert it to meters. This is going to be, I'm not sure, it's going to be probably category 4 or category 5 or something like that. I have to double check a couple of things to see if it falls into category 4. And because it's cast iron, this is not a smooth plate. And then, so I got to check Reynolds number. Let's see if I have all the information. I have the length, I have the width, I have the viscosity of water is given. I'm going to use the density of 1,000 kilograms per meters cubed for liquid water. I think I have everything. The first step in solving a problem like this is always calculating Reynolds L. Reynolds L would be rho times V times L over mu. And Reynolds is one that is non-dimensionalized, right? So kilograms per meters cubed times velocity is given as 1 meters per second times length, which is 0.26 meters in this case, and viscosity is 0.001567. You can go ahead and calculate the Reynolds number again. So this is the plate and the flow is going over it. And this is L and this is W, like this. The flow is parallel to L, right? That's what it is. If you calculate Reynolds number, I already calculated Reynolds number. It happens to be 165,864. This Reynolds number is less than 10 to the 6th. So if I want to, it's less than 5 times 10 to the 5th too. But because it is cast iron, you can't say this is laminar flow. No, this is not laminar flow. You have cast iron. It's a rough plate. Because it's a rough plate, it's going to be turbulent flow. So then we kind of check it for category 4. Category 4, if you remember, if you have watched the video, category 4 works if Reynolds number is more than 10 to the 6th. And there's another condition that we have to check, and we're going to check that condition too. But based on the Reynolds number that we have here, which happens to be 1.65864 times 10 to the 5th, this is less than 10 to the 5th, this is less than 10 to the 6th, so you cannot use category 4 at all. And because this is a rough plate, this already becomes, because it's a rough plate, if it was smooth, we could, fit it into category 1, actually, if it was a, smooth and, not trip boundary layer, stuff like that. So this is a rough plate. And because it's a rough plate, this is going to be a category 5. What was category 5? Category 5, if you remember from the video I posted, is a category that when the problem doesn't fit in the first 4 categories. And then you have to go to that graph. There's a graph that is the equivalent of Moody chart for external flow over a flat plate. We're going to go to that one, and we're going to pick the value for average friction coefficient from that one. That's the that's the case. But in order to use that graph, you need to calculate one more thing, and that was L over epsilon. I need to calculate that. So let's do that. L over epsilon, L is 0.26, is 0.26 meters, and this is and epsilon is 0.26 millimeters, which is 10 to the negative third. So L over epsilon becomes 1,000, like this. Now that I have the information, so I have Reynolds number, this is my Reynolds number, and this is my L over epsilon. I have these two values. With these two values in mind, I can go to that graph. And let's see what the graph is going to show. All right, this is the graph. This graph is like the holy grail in a way for external flow over a flat plate. It's the equivalent of the Moody chart for internal flow. This is that one. So let's see what we have here. What we have here is, if you take a look at the value of, Reynolds number, 1.65-ish times 10 to the fifth, that's the value that we calculated over there, is going to be somewhere here. That's going to be the value of Reynolds number. Okay, cool. And luckily for us, this problem, L over epsilon, actually is a number 1,000. So I have the graph for that one. So I'm not going to deal with a lot of difficulties in this case. So let's actually go ahead and draw a line from this point, that would be somewhere here, 1.65 times 10 to the negative, somewhere here, and it's going to cross this graph. This is our graph. That's the graph that we need to work with, basically. And here, and based on this, I can find the value for, let me just do this. There you go. I got something. There you go. So this would be the value. This, in fact, would be the value of, that would be the value for the friction coefficient in this case. So what value do you guess here? I guess the value that I can see here is somewhere around 0.007, a little below 0.007. So I'm going to go for a value such as, let's say CF is around like 0.0068-ish. That's the value I'm going to pick, because that looks like this is the value here. So we're going to go back to our notes, and we're going to pick this value, 0.0068, for the friction coefficient. Remember, this is category 5, and we cannot use the equation for category 4 for it. And after I solve this problem, I'm going to actually use that equation, which is incorrect in this case, and see, what the difference would be. So let's go back to our notes and see what the drag force will be. Okay, so the value from the graph that I picked, CF average from the graph, category 5, remember, was 0.0068. That's the value I picked. In order to calculate the drag force, we go back to the basic equation, the average friction coefficient times dynamic pressure, like this, times the area. Area in this case is basically 0.26 meters times 2 meters, from what I remember. Let me double check that to make sure that everything is good to go. Yes, that would be the value, and area becomes 0.52 meters squared. So the drag force becomes CF 0.0068 times 1/2 times 1,000 kilograms meters cubed times velocity. The velocity happened to be 1 meters per second squared, like this, times 0.52 meters squared. And eventually the drag force happens to be, for this particular case, would be 1.768 Newton. That's the value of the drag force. Here's one interesting question. What if somebody by mistake, uses the category 4? Well, you can see in this case, category 4, you can only use it when Reynolds number is more than 10 to the 6th, and epsilon over L is more than 10 to the negative 4th. Yes, in this case, epsilon over L is definitely more than 10 to the negative 4th, definitely. In fact, it is 10 to the negative third epsilon over L, right? So if I wanted to use category, 4, epsilon over L, which is basically 1 over L over epsilon, becomes basically 10 to the negative third, which is more than 10 to the negative fourth. But Reynolds number is not more than 10 to the sixth. So it's not category 4. So I cannot use, category 4. Category 4 is not going to work. In fact, Reynolds number is less than 10 to the sixth. So I calculated that. It would happen to be a value of 1.65864 times 10 to the fifth. All right, but what if somebody by mistake goes for category 4? What's going to happen? Let's write the equation for category 4. The equation for category 4, if you remember, is 1 point. This is wrong, so I'm going to just write it, use a different color so you know that this is wrong, so you don't get confused that this is solving the problem wrong. I'm going to write wrong equation. Okay, this is wrong equation. You shouldn't use this wrong equation. But what if somebody by mistake chooses this category, category 4? What's going to happen? 1.89 minus 1.62. Oh, this is CF. So let's write it as CF. Okay. CF wrong. I'm going to write wrong. This is wrong. Equals 1.89 minus 1.62 log 10 of epsilon over L, basically. Epsilon over L is that value that we got, is 10 to the negative third in this case. Negative 2.5, that's the power. I already, just in case, just to see what happens, I already calculated this and to see the difference. And the value that I got for this wrong, is equation is 0.0844. Now, so let's take a look at what the actual number is from the graph and what this value. The actual number from the graph happens to be this number. This is the correct value, apparently. So this is the correct value that we got from the chart, because it is category 5, 0.0068. And if by mistake you use that equation, you're going to find this incorrect value. That is incorrect. So you can see a difference that is actually not negligible that much. So CF correct happens to be 0.0068, and CF incorrect happens to be 0.0084. And these two values, there is a huge difference. There is a big error in this case. So this is where you realize that it's important to identify the problem, identify the category that when it comes to external flow over flat plates. All right, so thank you very much for watching this video. Again, I encourage you to subscribe to this channel, because every day I try to upload one video in the area of thermal fluids. And again, if you didn't watch the videos where I explained the different categories of, external flow over flat plate problems, go back and watch them. The links are in the description. Thank you very much. Have a good day.